In this problem, we are given the concentration of hydronium and we're being asked to determine the concentration of hydroxide. So our first priority should be try to establish a relationship between these two quantities. We have the water dissociation constant, Kw, which relates in the following way. Kw equals concentration of hydronium times concentration of hydroxide. At 25 degrees, that number will always be 1.0 times 10 to the minus 14. Now this actually simplifies our lives a lot, because doing a simple algebraic simplification, we can just take our Kw divided by our known value, which is hydronium, and we obtain hydroxide. Substituting the numbers, 1 times 10 to the minus 14 over 0.1 gets us the concentration of hydroxide at 1 times 10 to the minus 13. Which brings us to our next set of examples. Here we're dealing with concentrations of hydroxide, but we don't have the concentration of hydronium. Now we just have the pOH. For that, we will need to resort to this equation. px type equations, pH or pOH will always equal minus the logarithm of hydronium or hydroxide respectively. So in our case, we have hydroxide, so pOH would equal minus the log of whatever concentration we are given. In this case, 3.7 times 10 to the minus 5 will equal a pOH of 4.43. In our second example, 6.39 and 1.08 respectively. But what happens if instead of us being given the concentration of hydroxide, we're given the pOH? Well, our next example deals with that issue. When we have a px type function, so long as we know the base of the logarithm, our logarithms that we're working with by default are base 10, we can just say that the concentration of hydronium or hydroxide will be 10 to the minus pOH or pH respectively. So just 10 to the minus whatever number you're given, 4.91, 9.03, 10.55, will give us the concentration of the hydroxide. And that's pretty much all that is required in order for us to solve this type of problems.